Hello friends, welcome back to today's class. So in the previous class we had started with your color image processing things, and if you remember we had also seen the various palettes of your colors and how you get all your 256 colors RGB system, how you get your safe RGB colors, and all those things has been seen in the previous class. So if you remember, just a small recap of the previous class. So this is what is the palette I was speaking of. Here you can see all the colors of the RGB have been shown. Okay, and in the upper block diagram, that is in the upper table, you can see how it is represented with the help of the hex. This we have seen in the previous class as well. We have also seen that how do you merge all the three planes, that is R plane, G plane and B plane, and you get a RGB total image. R stands for nothing but red, G is green and B is blue. So all these things have been covered in the previous class. Moving ahead, today we'll go ahead with the next very important thing, which is nothing but your color image processing. So as you have seen already that your sienna, magenta and yellow, these are nothing but your secondary colors, which are alternative to the primary colors. So to give you an example, say for example you have a surface coated with sienna pigment, then you can see that it is completely seen as only white light. Say I have a wall which is painted with sienna, then it is completely illuminated by white light and you cannot see any red light. That means what now? The sienna subtracts the red light from the white light and then it shows only your white light, removing all the red light. So that means we can say something like that it is composed of equal amounts of green, red and blue lights, but the red will be subtracted. So it means that most of our devices, such as say your color printers, copiers, they require your sienna, magenta and yellow data input. We call it as CMY input. CMY input, which stands for sienna, magenta and yellow input. So who requires this CMY input? Your hardware devices such as your photocopiers or your color printers, all those things. Okay, now what is one major thing we require is whatever the input we give, whatever the input we'll be giving, whatever the input we feed, it will be in the form of R, G and B, right? But what your devices require? Your devices require your CMY. That means we need to convert your RGB into your CMY, right? So if I want to convert this, then there is one simple operation to convert it, which would be something like this. It is nothing but, I'll just write and show you. It is, I have an what is the requirement we want now? We want the CMY. So therefore in the form of a matrix, I'll be writing your C, M and Y, right? So this is my requirement in the form of a matrix, and from where I have to get them? I have to get them from the RGB. So that means I have to get them from where now? From R, G and B. Then how do you get this CMY from RGB? Just now I have given you an example. That is the example of a surface being painted by sienna. Then what is happening there? There we saw that only white color is getting reflected, whereas the red is getting subtracted. That is, it is being removed. So what we need now? If I want a sienna, I should 1 minus this RGB. So when I do 1 minus RGB, I will be getting your CMY, which is sienna, magenta and yellow colors. So this is a very simple operation, friends. You should do 1 minus the input. What is the input here? Input is your RGB is my input, and what is the required output? Output is your CMY. So I hope this is clear, friends. So similarly, let us assume that you want RGB. You want RGB and your input is CMY. I hope you are getting it. I am just reversing the condition now. Here the input is what now? RGB. Output is what now? CMY. Now I want the output as RGB and the input as CMY. Can we apply it? Can we get it? yes, that could also be got. What is the simple thing we need to do in that case? It is nothing but you need to subtract your RGB from CMY. That's all. You can say it is RGB minus CMY, something like that. If you do, then easily you can get your RGB. I want to say that, say your RGB values can be easily obtained from a set of CMY values by subtracting the individual CMY values from 1. So what we are doing, friends, we will be subtracting your CMY values from 1, then we will be getting what now? Your RGB values. So whatever you can see here in this figure, whatever the figure you are seeing here right now, it is nothing but your RGB safe color cube. I hope you might have already heard of your RGB safe palette. The palette has been replaced with the help of the cube now. Okay friends, so I hope this whole thing is clear, how to obtain your CMY from RGB, how to obtain your RGB from CMY, and why it is required. That all things have been covered. Okay, now we'll move ahead to the next thing now. So till now friends, we have seen your RGB system. Till now we have went through your RGB model. Now going forward, what we need to do is we need to come across your CMY model. That means what we are doing now, we need to change our RGB model into a CMY models. Why it is required? Because as simple reason for all your hardware implementation. Okay, now unfortunately, what is happening is the RGB, CMY and all other similar color models are best suited for describing the colors, especially in the terms of your human interpretation. Say for example, you have a color, say of an automobile, then how do you tell the color? Will you tell it by giving the percentage of the composition of its color? No. How do you give it? We do not think of any color image that it is composed of only 3 images, right? Like say for example, I show you a color photo. Do you think that it is made up of just red, green and blue? No. But what we humans view, we view them as an color object. Like say for example, if I show you a red car or a maroon car, you would say, oh, it is a maroon car, or rather you would not say it is a mixture of 3 colors such as R, G and B. So therefore we human beings try to get your thing with the help of a color object. And how do you describe this color object? This color object is described with the help of hue, saturation and brightness. So how do you tell it? With the help of the HUE hue and your saturation, SAT saturation, and finally your brightness. Okay, so I would say it is H, which stands for hue, S which stands for saturation, and B which stands for brightness. That means we human beings try to describe a color object with the help of these 3 main components, which is H, S and B. And I hope friends you have already studied this in the previous sections as well. I hope so. I only have covered this thing. Okay, so what is hue, friends? You can just pause for a while and you can just check out what is hue. Anybody? So what is hue actually? Hue is nothing but it describes how pure is my color. Hue, it describes how pure is my color. Like say for example, you say it's a red car. That means it's purely red. Say for example, it's a maroon car. It means that it's not completely red, but it has been mixed with something, right? So therefore, hue describes how pure is my color. Next comes is your saturation. What could be saturation? Again, this was covered in the previous few lectures ago. So saturation is nothing but it tells you to what degree the pure color is diluted by white light. Like say for example, I have a red color. Okay, so to this red color, how much amount of white light you have added to it and you have diluted the red color. That's why we say dark red, light red, or you have some pink variants, pink, baby pink, dark pink and so on. So what it is nothing but it is totally based on your saturation levels. Next comes is your brightness. As I was telling you, it is H, S and B. So we have covered H and S. The last remaining is your brightness. So what is brightness then? We have also described this brightness. we say that brightness is very difficult to measure. That's why we have two notations. One is we have two versions. One is chromatic and achromatic. If I have achromatic, then this brightness is nothing but is your intensity. If I have a achromatic image, it becomes intensity, and this intensity becomes one of the key factors for describing the color sensation. That is, what is the color sensation actually. Now we also know that the intensity is most useful descriptive for monochromatic images. Say for example, I have a monochromatic image, then this gray level tells us how measurable or how easily it could be interpreted. So therefore we come across a model here right now which I call it as HSI model. Remember friends, what did we study initially? What did we study initially? We studied HSB. I told you we will be, just remember these three alphabets, which is HSB. B stands for brightness. This brightness has been removed and it has been replaced by I. Why? Because intensity is nothing but it is a measure of your brightness. That means we are now studying what model? HSI model. H stands for hue, H stands for saturation, I stands for intensity. Now this HSI model is different from your basic RGB model. Okay. Now this HSI model is nothing but it is an ideal tool for all your image processing algorithms. Say for example, I want to write any image processing algorithm which is based on color descriptions, then this HSI model forms the basics of this all the image processing algorithms. So we can say that, or we can summarize that RGB is for color generation, HSI is for color description. So if I want to describe any description is required of any color, then we say that it is HSI model. But if you want to generate any color, say for example you have a image captured by your color camera or by a monitor, then we require your RGB. If I want to generate an image, that is color image, then you require RGB. And if you want to process an image based on the descriptors, that is nothing but if you want to do any color description, we require your HSI model. Now based on these discussion friends, whatever we have went through now, we'll move to the next very important thing. As you can observe in this diagram here, one second, yeah, as you can observe in this diagram here friends, so this diagram is trying to give you a relationship between your RGB and HSI color models. Okay, now if you observe this carefully, we already discussed in your previous classes that your RGB is used as three monochromatic intensity images. Which are the three monochromatic intensity images? It is nothing but red, green and blue. So therefore you know that we would like to extract the intensity from an RGB image. Now if you see this below figure, which is figure 6.12, the first one, you can see that there is a line which is joining the black and white vertices, and which is a vertical line. You can see there is a line which is joining your black and white vertices. You can just, I am showing you. So this dotted line, what are the dotted line you can see here? This is the line which is trying to join your black and white. So this line which is joining gives you the intensity axes. Okay. Now, so say for example, in the below figure, we just want to pass a plane perpendicular along the intensity axis. So whatever the line you have drawn now, white to black, I have shown you just now. If I want to pass a plane perpendicular to this intensity axis and containing the color point, then the intersection of the plane with the intensity axis would give you the range from 0 to 1. Okay. So that means when you pass a perpendicular plane along the axis, what you actually note, it is nothing but as you go on passing the plane, it becomes a function of the distance from the intensity axis. So the color goes on increasing as you go on passing the plane. So if you want to see this, then what we'll be doing is a plane will be there which would be defined by 3 points. Which are the 3 points now? It is nothing but black, white and cyan. And the fact that the black and white points are contained in the plane also tells us that intensity axis is also contained in the plane. Okay, now when we arrive, so therefore we can say that we would be arriving at the conclusion that all three colors, whatever the colors are generated, all the colors are generated by these three colors which lie in the triangle defined by these colors. You can observe here in the 6.12b that there is a triangle which is being done whenever you pass a perpendicular line, and all the colors we get from this perpendicular plane. Therefore, from these concepts we can say that the hue, saturation and intensity values are required to form a HSI space. And how you get this HSI space? This HSI space is got with the help of the RGB color cube. So therefore we can say that we can convert an RGB point to a corresponding HSI color model just by working on the geometrical formulas, which would give us what would be the preceding decisions. So therefore the key point which we need to keep in mind here is the 6.12 figure and its corresponding HSI color space tells us that here the vertical intensity axis and the locus of color points both lie on planes which are perpendicular to the axis. Okay friends, so this is all regarding today's class, wherein we have started with your HSI model and we have also tried to understand how the RGB model could be connected with your HSI model. Okay, so the rest of the things I will continue in the next class. We'll try to dig more deep into these things in the next class. Till then, if you have any doubts, you can call or WhatsApp me. If you have any problem also, you can just drop a message. Thank you for listening to the video. We'll meet again in the next class.